suppose we want to integrate in polar coordinates. Now we have the following conversion formula. So if you have a double integral in Cartesian coordinates or rectangular coordinates, then you can convert that double integral by using your conversions. X equals r cosine of, x equals r cosine of theta, y equals r sine of theta. Okay, so you substitute that in for your x and your y. But notice our formula also has this extra factor of r here. So whenever you convert to polar coordinates, you always have to multiply your function by r. Now the reason for this is because of what we call polar rectangles. So when we convert to polar coordinates, what we're doing is we're taking our surface and we're breaking, or our domain or our region, and we're breaking it up into what we call polar rectangles. Okay? And because of theta, and we have this angular thing going on, these polar rectangles are not perfect rectangles. Notice they have a little bit of curve to them. Okay? Whereas if we were back in Cartesian coordinates or the rectangular coordinate system, we just had squares, right? We took our region D and we broke it up into a bunch of squares, and it's easy to calculate the area of a square, right? It's just length times width. Okay? But now that we have this curve there, it's a little bit more complicated than that. Okay? In fact, the area of a polar rectangle is approximately, okay, it's not going to be equal to, but it's close enough. It's equal to the following. So notice that this distance right here, this is approximately delta r, ri plus 1 minus ri, okay? And using the arc length formula, this distance right here is not just delta theta, it's actually r times delta theta, and that's where arc length is coming from. So the area of this polar rectangle is approximately r, and I'm going to shift things around a little bit, delta r, delta theta. Okay? And that's why we get that extra factor of r right there. It's because our polar rectangles have slightly more complicated areas. Okay? Now again, your book goes into that more precisely, but I want to give you sort of the general idea, and this is it. That's why we have that extra factor of r. Our polar rectangles are slightly more complicated in this coordinate system. But now we have that conversion, we can actually solve double integrals. Now I recommend using polar coordinates when your domain or your region is circular in some way, and if you can actually integrate like we saw in that earlier example by hand. Polar coordinates could be a good and viable technique. But in any case, let's go and see how to do this. So our region D is all the points x, y such that x squared plus y squared is less than or equal to 4. So if we draw that, all that is all the points that are inside and on a circle of radius 4. Remember that equation there, x squared plus y squared, that's giving you a circle centered at the origin, and that 4 is giving us radius 4. So our region in this case is all of this. Okay? So then the double integral with respect to d of x plus y dy dx. I'm sorry, not dy dx. Oh, no. Continue. Go back. This should be dA, not dy dx. Going crazy here. This is equal to, okay, double integral, and we'll talk about the bounds in a second, r cosine of theta plus r sine of theta, and remember, we have to multiply by an extra factor of r dr d theta. All right, now what about the bounds, though? Okay, so let's look at our region here. Remember, it is this filled-in part, okay? And I want you to think about what radius do we need, or radii, I should say, do we need, and what angles do we need to get this whole circle here? Well, notice r, for any point here, r is going from 0 to 4, okay? And to get the entire unit circle, I'm sorry, not unit circle, in the entire circle, theta has to go between 0 and, with a full revolution around a circle, 2 pi. Okay? So that would be our parameterization of this circle here. R is going from 0 to 4 because we have the whole circle here. Okay? And to get the full revolution of the circle, theta needs to go between 0 and 2 pi. So now we can solve this. This is equal to hopefully we can solve this at least. Let's go ahead and distribute the r before we do anything fancy. So we'll get r squared cosine of theta plus r squared sine of theta. Alright, so that was by multiplying r. Now let's go ahead and factor out r squared. I'm going to do that in one move here, so I save a little bit of space. Okay, and so now notice this part here in the front, r squared, that's the only part that has an r squared, and the rest of it has theta, so we can sort of treat this as a constant and do our partial integration like we've been doing over and over again. So this integral will be r cubed over 3. I'm going to put here evaluated at 4 and 0 times cosine of theta plus sine of theta d theta. Okay, and that's going to give us, let's see, so 4 cubed is 64, right? So it'll be 64 over 3 times the integral from 0 to 2 pi cosine of theta plus sine of theta. So now we have a nice little Calc 1 integral. This is 64 over 3 times, so what's the antiderivative of cosine? That is sine minus cosine of theta, evaluated at 2 pi and 0. And if we plug that in, we'll get, please PowerPoint, well, I'm almost done. 64 over 3. If we plug in 2 pi, we're going to get 0 minus 1. Okay. Minus, if we plug in 0, we're going to get 0 minus 1. And we actually get 0 from this.